You think empty space is empty? Not approximately wrong, fundamentally, completely, absurdly wrong. Look around right now. Between you and that wall, between your atoms, between everything you see nothing. Vacuum, emptiness, the absence of stuff. Here's a simple question. What's in that empty space? Go ahead. Answer it. You can't. Because everything you think you know about nothing is preventing you from understanding what's actually there. You've been calling it empty your whole life. You've walked through it, breathed it, existed in it, and you have no idea what it is. The universe is playing a trick on you. The biggest trick, empty space, the thing you think is the absence of everything, is seething with activity. Violent, constant, measurable activity. Fields are collapsing and reforming. Particles are appearing and vanishing. Energy is fluctuating at scales and speeds that would terrify you if you could see them. Right now, in the empty space between your eyes and this screen, virtual particle pairs are being created and destroyed, approximately 10 circumflex 43 times per second per cubic centimeter. You don't feel it, you don't see it. But if physics is right, and we've tested this to absurd precision, it's happening. So let me ask again, what's in empty space? The answer will break your conception of reality. Because once you understand what Feynman understood, you can never look at nothing the same way again. Let's start with something you can actually do. Take your hand, hold it in front of you. Now move it through the air. You feel resistance, right? Tiny, but there. That's air molecules bouncing off your skin. Makes sense. There's stuff there. Nitrogen, oxygen, water vapor. You're pushing through matter. Now imagine we pump out all the air. Perfect vacuum. Put your hand in that space and move it. What do you feel? Nothing, right? Because there's nothing there. Wrong again. Even in perfect vacuum. No atoms, no molecules, no particles of any kind. Your hand is still interacting with something. Electromagnetic fields, gravitational fields, the quantum vacuum itself. Here's what nobody tells you in school. Fields aren't abstractions. They're not mathematical conveniences. They're real physical entities that exist in space. They have energy, they have momentum, they can do work. Move a charged particle through empty space, and it radiates. That radiation comes from somewhere. It comes from the electromagnetic field that permeates every cubic centimeter of the universe. So empty space isn't empty. It's filled with fields. But that's just the first level. That's the answer that seems satisfying until you think about it for 10 seconds. Because now you have to ask, what is a field? This is where it gets interesting. For thousands of years, humans believed in action at a distance. The sun pulls on the earth, magnets attract iron, no mechanism required. Things just acted on each other across empty space. Newton hated this, absolutely hated it. When he published his law of universal gravitation in 1687, he knew he was describing how gravity behaved, inverse square law, proportional to masses, specific force at any distance. But he had no idea how it worked. In his own words, the idea that one body could act upon another at a distance through a vacuum is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. He was right to hate it. Action at a distance is absurd. So what's the alternative? Fields. The idea emerged slowly. Michael Faraday in the 1830s and 1840s wasn't a mathematician. He was an experimentalist, brilliant with his hands, terrible with equations. He couldn't work through the mathematical formalism that other physicists used. So he invented a different way of thinking. He imagined lines of force, physical things that existed in space around magnets and charges. Move a magnet, and those lines moved. They had tension, pressure, reality. The lines weren't just descriptions of what would happen if you put a test charge there. They were the mechanism. James Clerk Maxwell in the 1860s took Faraday's intuition and made it mathematical. His equations, 4 elegant statements that unify electricity and magnetism, describe how fields behave. Change an electric field and you create a magnetic field. Change a magnetic field and you create an electric field. The equations are coupled, dynamic, alive. And here's the kicker. When Maxwell worked through the mathematics, he found that his equations predicted waves. Electromagnetic waves traveling through empty space at a specific speed, 299,792,458 meters per second, the speed of light. Light isn't a substance traveling through space. Light is the electromagnetic field oscillating. Space itself, empty space, is capable of sustaining these oscillations. Think about that for a second. When you see light from a distant star, you're not receiving particles that traveled across billions of kilometers of nothing. You're detecting oscillations in the electromagnetic field that fills all of space. The field is already there. It's always there. Light is just the field waving. So empty space is filled with fields: electromagnetic field, gravitational field, electron field, quark fields, Higgs field. Every fundamental field permeates every point in space, always. But we're still not at the bottom, because now you have to ask, what is the field when nothing's happening? What's the electromagnetic field doing in a region where there are no charges, no currents, no light passing through? Common sense says nothing. The field is zero, dormant, waiting to be activated. Quantum mechanics says wrong again. Here's where Feynman's explanation becomes insane. In quantum mechanics, you can't specify both the position and momentum of something with arbitrary precision. Heisenberg's uncertainty principle, you've heard of it. You probably think it's about measurement. We disturb things when we measure them. No, it's not about measurement, it's about reality. The universe itself doesn't have definite values for position and momentum simultaneously. That's not a limitation of knowledge, that's a property of existence. Now apply this to fields. Fields have energy. Energy is related to how much the field is displaced from zero and how fast it's changing. In quantum mechanics, you cannot simultaneously specify the field value and its rate of change with perfect precision, which means the field cannot be exactly zero. Even in vacuum, perfect empty, no particles anywhere vacuum, the quantum fields are fluctuating. Not because something is causing them to fluctuate, because quantum mechanics forbids them from being exactly still. This isn't speculation, this is measurable. Take two metal plates, make them extremely flat, extremely clean, put them very close together, micrometers apart, in a perfect vacuum. No air, no particles, nothing between them. What happens? They attract, not because of electrostatics. The plates are neutral, not because of gravity. The force is way too strong. They attract because the quantum vacuum between them is different from the quantum vacuum outside them. This is the Casimir effect, predicted by Hendrik Casimir in 1948, measured precisely dozens of times since. The vacuum fluctuations outside the plates include all possible wavelengths. The vacuum between the plates can only support fluctuations with wavelengths that fit between the plates. You can't have half a wave sticking out. Fewer fluctuations between the plates means less energy density. The vacuum outside pushes harder than the vacuum inside. Empty space exerts pressure. We've measured it. For plates 1 micrometer apart, the pressure is about 1.3 pascals. Tiny but real, measurable, exactly matching quantum predictions. Let me say that again. The nothingness between the plates is measurably different from the nothingness around the plates. Empty space has structure, but we're still not done. Because the deepest insanity is this: the vacuum fluctuations aren't just theoretical conveniences. They cause measurable permanent changes to matter itself. Consider an electron, basic particle, negative charge, spin 1/2. According to classical physics and even basic quantum mechanics, the electron is a point particle. No size, no structure, just charge and mass concentrated at a point. But point particles in quantum field theory have a problem. The electromagnetic field around a point charge becomes infinite at zero distance. Infinite field means infinite energy. Infinite energy means nothing makes sense. So what's actually happening? The electron is surrounded by vacuum fluctuations. Virtual particle pairs, electron and positron, are constantly appearing and disappearing around it. These virtual particles interact with the real electron's field. The negative virtual electrons are repelled slightly. The positive virtual positrons are attracted slightly. This creates a cloud of virtual particles that screens the electron's charge. If you measure the electron from far away, you measure the screened charge. If you measure from very close by, scattering high-energy particles off it, you measure a stronger charge because you're getting inside the screening cloud. We've measured this at distances around 10 circumflex 18 meters, the electromagnetic coupling constant. Basically, the effective charge increases by about 3%. The vacuum is changing the properties of particles. But here's where Feynman really drives it home. When you calculate the energy of the vacuum, add up all the zero-point energy from all the quantum fields fluctuating in all of space, you get infinity, literally, infinite energy density. Obviously, that's wrong. If vacuum had infinite energy density, the universe wouldn't exist. Gravity would collapse everything instantly. So we must be calculating something wrong. But what? Nobody knows. This is one of the deepest unsolved problems in physics. The vacuum energy calculation gives a number that's off by a factor of 10 circumflex 120 from what we observe. That's not a little wrong. That's the worst prediction in the history of science. We can measure vacuum energy. It's called the cosmological constant, and it's related to the accelerating expansion of the universe. The value is tiny, about 10 circumflex 9 joules per cubic meter. But quantum field theory predicts 10 circumflex 111 joules per cubic meter. Something is catastrophically wrong with our understanding. And yet, and this is crucial, all the other predictions of quantum field theory work perfectly. The magnetic moment of the electron matches experimental measurement to 11 decimal places. The Casimir effect matches predictions exactly. Quantum electrodynamics is the most precisely tested theory in all of physics. So the vacuum fluctuations are real, the calculations work, but the total energy is wrong by 120 orders of magnitude. Think about what this means. Empty space is not only not empty, it's filled with violent quantum activity, measurable forces, particle screening clouds, and we don't understand the most basic thing about it. We don't know why it doesn't have infinite energy. We don't know what mechanism sets the actual energy density. We don't even know if the question makes sense. Let's go further, because if you really want your brain to hurt, consider this. According to general relativity, energy and mass curve space-time. That's gravity. More energy means more curvature. If vacuum has energy, which it does, we measure it, then vacuum curves space-time, which means empty space is not flat, even with no matter, no particles, no nothing. Space itself has curvature. You're sitting in curved space right now, not because of Earth's mass, not because of the sun, because the vacuum itself has energy. And it gets weirder. Virtual particles, those electron-positron pairs appearing and disappearing in the vacuum, can become real under the right conditions. Put a strong electric field in vacuum, strong enough, and it rips the virtual pairs apart before they can annihilate. The electron goes one way, the positron the other. They're now real particles. You've converted vacuum energy into matter. This is called the Schwinger effect. The required field strength is enormous, about 10 circumflex 18 volts per meter, but we're getting close to testing it with high-powered lasers. Empty space can be torn apart to create matter. Or consider black holes. Stephen Hawking showed in 1974 that quantum fluctuations near a black hole's event horizon cause the hole to radiate. A virtual pair appears near the horizon. One particle falls in, the other escapes. To an outside observer, the black hole is emitting particles. Where's the energy coming from? The black hole's mass. The vacuum fluctuations are converting black hole mass into real particles. Given enough time, an absurdly long time, 10 circumflex 67 years for a solar mass black hole, the black hole evaporates completely, all because empty space isn't empty. Now think about the early universe. Right after the Big Bang, the universe was hot, dense, filled with energy. As it expanded and cooled, particles condensed out of the quantum fields. But what's the difference between a particle and a field? There isn't one. In quantum field theory, particles are excitations of fields. An electron isn't a thing separate from the electron field. It's a localized excitation, a ripple, a wave packet in the electron field that fills all of space, which means every particle in your body, every atom in the universe is a manifestation of quantum fields vibrating in space. You're not made of particles moving through empty space. You're made of space itself vibrating. The table you're sitting at, vibrations in quark and electron fields, the light hitting your eyes, vibrations in the electromagnetic field, the gravity holding you to Earth, curvature of space-time, which is itself a field. Everything is fields. Fields are everywhere. There is no empty space. There never was. So when you ask what's in empty space, the answer is everything. Every possible field, every possible fluctuation, every possible quantum state exists in superposition in every cubic centimeter of the universe. The vacuum is the most complex, active, energetic, mysterious substance, if we can even call it that, in existence. And here's the final kicker. We use this. GPS satellites work because we can calculate time dilation from general relativity, which requires understanding how mass energy curves space-time, which includes vacuum energy. Particle accelerators create matter by dumping energy into quantum fields in empty space. MRI machines manipulate the magnetic fields permeating vacuum. Computer chips rely on quantum tunneling, particles passing through classically forbidden regions, which only makes sense in quantum field theory. Every piece of modern technology is built on our understanding that empty space isn't empty, but we still don't know what it is. We can calculate how it behaves, we can predict what it does, we can measure its effects to absurd precision, but we don't know why vacuum energy is the value it is. We don't know how to make general relativity and quantum mechanics agree on what vacuum means. We don't know if space is fundamental or emergent. We don't know if the fields are the deepest level or if there's something beneath them. This is where the chain ends for now. Feynman understood this better than anyone. He built quantum electrodynamics, won the Nobel Prize for it, spent decades teaching it, and he was the first to admit we don't know what fields are. We have equations that work. We have predictions that match measurements. We have a framework that explains everything from chemistry to cosmology. But at the bottom, when you ask what is a field, the honest answer is we don't know. We can describe how they behave. We can calculate what they do. We cannot explain what they are. It's not a failure. That's physics. You wanted to know what's in empty space. Now you know. Fields, quantum fluctuations, virtual particles, energy, structure, complexity beyond anything you imagine. You also know what we don't understand, why the energy isn't infinite, what sets its actual value, what happens when you combine gravity and quantum mechanics, what space itself is made of. The next time you look at the space between your hands, remember you're looking at the most mysterious, powerful, fundamental aspect of reality. It's not nothing. It's not simple. It's not understood. It's the vacuum. And the vacuum is where the universe does its most profound work.